Hello, today we will talk about calorimetry dosimeter and contains working principle, properties, dose determination, clinical application, and advantages and disadvantages. Are you ready? Let's start. Calorimetry is the most fundamental means of establishing the primary standard for observer dose. Calorimetry is an absolute method of dosimetry in which nearly all of the radiation energy received in a thermally separated mass is transferred into heat and qualified. The quantity observer dose is a term or describe how much energy ionizing radiation deposited in a substance. It is defined the amount of energy observed per unit mass and is measured in gray. The observer dose is affected by the radiation field as well as the substance with which it interacts. A broad number of applications utilizing ionizing radiation need knowledge of the observer dose. But radiation treatment is the more determining in terms of precision. The absorber dose to water is estimating as a first step of estimating the dose to tissue for some well-defined reference share. Water was selected because its radiation absorbed properties are similar to those of tissue. In radiation dosimeter, there are two types of calorimetry that are commonly used to measurement of fundamental values. One, the absorber dose calorimetry is used to determine how much energy is absorbed in any area. Two, the total absorption calorimetry is used to determine the amount of energy or power given by a collimated beam or the amount of power emitted by a radioactive source. A calorimetry is a primary instrument, which means that measurements taken with it are directly connected to non-physical variable. The reaction is independent of a characteristic such as dose rate and incoming radiation spectrum, especially in metallic calorimetry. Measurement with a secondary equipment such as ionizing chamber are on the other hand influenced by radiation condition, as well as other variables. A calorimetry as a aqueduct radiation environment can be used to calibrate it, such as a secondary dosimetry.
Next, we are going to discuss the working principle of the calorimetry. The calorimeter is primarily made up of a cubic water body, which is 30 centimeters long, and it is coated around 8 centimeters thick polystyrene since it operates at a water temperature of 4 degrees Celsius. The calorimeter detector can be placed in the water model at various depths corresponding to the radiation entrance window. For example, 5 cm under 60 degrees Celsius irradiation. The calorimeter is housed in a 1 meter long heat insulated enclosure, and the air temperature is actively controlled to 4 degrees Celsius to maintain temperature stability. The aerator on the inside wall of the housing allows water to circulate around the actual calorimeter, resulting in a consistent temperature in the calorimeter. A calibrated thermometer with a diameter about 0.25 millimeters is inserted into the tip of a thin conical glass pipette to measure the temperature rise due to the radiation in the water, which is roughly 0.24 millikelvin per gray. The total length of the pipette is around 110 millimeters and with a minimum diameter of 0.5 millimeters. Two of these temperature sensors are fitted at a distance of roughly 8 millimeters apart in a glass cylinder filled with ultra-pure water with 95 millimeters in diameter and the height of 41 millimeters, while the wall thickness with 0.7 millimeters and 2.5 millimeters. The detector is mounted on the water-filled phantom of the calorimeter using a metacrylate frame at the proper measurement depth so that the incoming radiation is parallel to the cylinder's axis. The figure depicts the calorimeter's major components. It's made to work with horizontal radiation beams. The water is placed in a 30 cm by 20 cm lucite tank, and 5 cm thick polystyrene foam is used to insulate the tank outside wall. The magnetic stirrer is used to stir the water in the water tank's bottom. The water tank cover contains many holes through which platinum resistance probes are placed to monitor the temperature of the water. The cover also guarantees that the water surface has free-flowing air gap. The radiation field enters through a window in the storage tank that is 3 mm thick and 12 cm by 12 cm wide. The windows are insulated with 5 cm thick polystyrene panel that can be removed. The temperature is controlled by a fan and a heat exchanger, and the phantom calorimeter is set in an insulated wooden box with the size of 85 cm on each side. To improve the working temperature change process of the water in the calorimeter, the cooling liquid can also be transferred through the heat exchanger in the water tank. The calorimeter may be used at temperatures ranging from 0 to 25 degrees Celsius. It usually takes 3 to 4 hours to set the temperature to 4 degrees Celsius at the beginning from room temperature. The temperature of the fluid in the heat exchanger is controlled by a bath that is maintained at 0.1 degrees Celsius. The temperature of the air moving around the calorimeter is monitored by an additional calibrated platinum-resistant probe.
Graphite calorimeters are electrically calibrated by depositing a known amount of electrical energy into the core. Water calorimeters offer more direct determination of the absorbed dose to water at the reference point in a water phantom. Water calorimeters are calibrated through the calibration of their thermistors in terms of the absolute temperature difference. Calorimetric methods can be classified also as isothermal. Ideally, adiabatic calorimetry requires no heat exchange between the absorber and the surroundings. To ensure adiabatic conditions experimentally is always problematic, and thus so-called quasi-adiabatic conditions are achieved resulting. Calorimetry is frequently used to calibrate chemical and solid-state dosimeter devices, but it has seldom been employed for routine dose monitoring until recently. However, when electron accelerators were more widely used in radiation processing, the usage of so-called process calorimeters became more important. Two types of calorimeters are used in radiation dosimetry, which is the total energy. The temperature of the calorimeter can be measured either during irradiation or before and after irradiation.
When we say dose determination must refer to main point, water calorimetry calibration difficult. Calorimetry is the most fundamental method of realized the primary standard for absorbed dose since temperature rise is the most direct consequence of energy absorbed in a medium. Graphite in general ideal material for calorimetry since it's of low atomic number and all absorbed energy repairs as heat without any loss of heat in other mechanisms such as heat defect. Water calorimetry is most direct method to determine dose. Water and water calorimeter are operated today as absorbed dose primary standard for cobalt-60 radiation as well as for high energy photoradiation. Use determine the absorbed dose to a graphite in a graphite phantom. The conversion to absorb dose to water at the reference point in water phantom may be performed by application of the photon fluence scaling or by a measurement based on cavity ionization. The absorbed dose to water and are used in clinical dosimetry can be calibrated directly in terms of dose water. One common method used today to determine dose water in medium energy X-ray is to make use of air kerma, calibrated ionization chamber, and to apply several conversion and correction factors. Reference conditions and additional water calorimeter has been developed for application and has now been operated in medium energy X-ray with energy potentials from 70 to 280 kiloelectron volt. Whereas of the difficulty of making measurement in Rontgen above 3 million electron volt in this energy range, reliance is usually placed on sample chamber of no volume and composition, and the exposure dose in Rontgen is calculated from a measurement of ionization product in the chamber by use of the Bragg-Gray formula.
Calorimeters of various types have been used in radiation dosimetry for more than 60 years. Calorimetry is currently the basis of primary standards of absorbed dosage in many nations throughout the world. Due to various technical advancements during this time, the idea behind these pieces is that when radiation interacts with a substance, the temperature in the absorbing medium rises dramatically. Calorimetry is the most accurate and direct way of measuring radiation dosage. According to several sources, calorimetry is the recommended method for clinical proton beam dosimetry. International Atomic Energy Agency recommends employing an ionization chambers with an absorbed dose to water calibration factor, or alternatively, a measured beam quality correction factor for dosimetry in the clinical proton beam. Despite this, there are currently no long-term calorimetric-based main standards for protons. The use of calorimetry for dosimetry of therapeutic high-energy proton beams, as well as comparably low-energy beams, has been established. A variety of calorimeter investigations were used to analyze the chemical heat effect in water and graphite. The average energy required for protons to make an ion pair in dry air has been determined by comparing ionization chambers dosimetry with water calorimeters. On the other hand, the availability of calorimetry for low-energy protons beams used to treat ocular melanoma has not been explored, owing to the narrow range of these beams and their restricted lateral extension. Clinical reference dosimetry of high-energy photon, electron, proton, and heavy ion beams in radiotherapy is based on absorbed dose to water standards. The usage of ionization chambers calibrated and a reference beam quality is frequent. The world's main and secondary standards dosimetry labs have been heavily involved in the development of these codes of practice as well as the provision of traceable measurement data.
Advantages. There are many advantages of calorimetry. 1. Any dosimetric technique that measurement at temperature range comes closer to the being direct. 2. They can be made absolute either instrument by means of electrical heating calibration. 3. Calorimetry are responsibility resistant to radiation damage at high doses. 4. Calorimetry have no LET dependence since ionic recombinations is irrelatively to the temperature raise. On the other hand, there are many disadvantages of calorimetry. 1. Radiation-induced endothermic or exothermic reaction in some material. 2. The calorimetry aperture is frequently big and difficult to carry out setup due to thermal insulation and instrument for thermal control and measurement. 3. Thermal leakage into and out of the calorimetry sensitive volume restrict the accuracy and the precision possible at low dose rate. 4. Calorimetry is limited to very high dose. On the